What's going on, guys? Justin here, and welcome to our 11th example video following our course on differential equations. Now, today's video is going to be on the method of undetermined coefficients. So let's go ahead and get into our general solution method for these types of problems. Okay, so our goal for today's video is to be able to solve equations of the form ay double prime plus by prime plus cy is equal to e to the power kx times some polynomial p of x. So the two things I really want you guys to key in on when we're approaching a problem of this form are this k here in this power of e, and specifically the degree of this polynomial of p of x, because those are the two things that are going to come to bear on our guess that we're going to make for our solution y sub p. Now, these three cases are split up based on the variation in our k there and the exponent of e. So the first case is if k is not a root of the characteristic polynomial ar squared plus br plus c equals 0. Now, we talked about characteristic polynomials in the last video, but it shouldn't be hard to see how this is constructed. We take the coefficients of each of our terms in the above equation and equate them to a quadratic. So what we're going to want to do is check our k against the roots of the characteristic polynomial, and then we will proceed with each of these cases. If k is not a root at all of the characteristic polynomial, then we will use the substitution e to the power kx times q of x, where q of x is kind of a general polynomial that's of the same degree of p of x. So if p of x is some quadratic, then we'll write q of x as ax squared plus bx plus c. Now for our second case, we have where k is a single root of ar squared plus br plus c. If it is a single root, we will add an x in front of our terms there, and if it is a double root, we will add an x squared there. So let's go ahead and get into a few examples so we can demonstrate how we're going to go about doing these substitutions. So number one says, find the general solution for the following equation, and then we have y double prime minus 7y prime plus 12y is equal to 4 times e to the 2x. So it's worth noting that in this case our k is equal to 2, and we can see that the degree of our polynomial, or our p of x, attached to that e to the 2x term is just 4, so it's a constant. So our degree is sort of degree 0. So this part tells us what degree of a polynomial we need to attach to our e term, but we need to see if we need to add any x's there. So we need to check to see if this 2 is a root of the corresponding characteristic polynomial. So that would be r squared minus 7r plus 12. And we can easily see that that is going to factor like this. We'll have r minus 4 times r minus 3, which gives us the roots r equals 4 and r equals 3. And 2 does not equal either of those. So that means we don't have to worry about attaching an x. So we're going to guess the following solution. So we will have y sub p is equal to, we will have no x because it's not a root. So we'll have e to the 2x times a polynomial of the same degree of what's attached to our e term, but we didn't actually have a polynomial, we just had a constant, so we'll leave a to denote that constant there. So we're going to let that be our substitution for our guessed solution. So let's go ahead and take some derivatives of this so we can make a proper substitution. So if we take the derivative, we'll get y prime sub p is equal to, well, that 2 will come down from the e, and we'll just get 2a times e to the 2x. And as you might imagine, if we take a second derivative, we'll get the same kind of action going on. So y double prime is going to be equal to 4a e to the 2x. This makes our substitution rather easy. So let's substitute these into our differential equation. We will have 4a e to the 2x minus 7 times 2a e to the 2x. And that's all going to be plus 12 times e to the 2x times a. And that is equal to 4e to the 2x. So we can go ahead and cancel out all these e to the 2x terms from all this. And we'll be left with 4a minus 14a plus 12a is equal to 4, which just leaves us with 2a is equal to 4 and a is equal to 2. So that means our solution, once we substitute that back in, y sub p, our particular solution is 2e to the 2x. Now, our general form for these types of equations, so our general solution is going to be y is equal to y sub p, our particular solution, plus c sub 1 times y sub 1 plus c sub 2 times y sub 2, where this y sub 1 and y sub 2 are the roots to the corresponding homogeneous equation. So that would give us the final general solution for this as y is equal to, well, let's see what our solution to y sub p there was. It is 2e to the 2x plus c1 times, if you remember, our roots are 3 and 4, so we'll have c1 times e to the 3x plus c2 times e to the 4x, and that will be our final general solution for this differential equation. Now, as finding the fundamental set of solutions for the corresponding homogeneous equation is what we did in the last video, from here on out, we are just going to be trying to find a particular solution of the differential equation. And then if you want, you can take it upon yourself to go ahead and turn that into a general solution. But let's go ahead and get into our next example. So our next example is find the general solution for the following equation. We have y double prime minus 8y prime plus 16y is equal to 2e to the 4x. So once again, we can see that we have a constant here. So the degree of our polynomial p there is going to be 0. Now let's go ahead and find the roots to this characteristic polynomial. So we'll have r squared minus 8r plus 16 is equal to 0. But that, of course, is equal to r minus 4 squared. So that means we have a double root of 4. But if you notice, our k here is also 4. So that means we will use our formula for when we have a double root. So our particular solution, y sub p, is going to be equal to ax squared times e to the 4x. And next we are going to take derivatives so we can make our substitutions. So we want to find y prime here. So we're going to have to do that by the product rule. So let's go ahead and take the derivative of this first part first. So we'll have 2ax times e to the 4x. That's going to be plus the derivative of that e term, which will just bring a 4 down. So we'll have 4ax squared e to the 4x. So that's just our first derivative there. And our second derivative, we're going to also have to take the product rule. So let's start with this first term here. Well, our x will disappear and we'll be left with 2a times e to the 4x. That's going to be plus the derivative of our e terms. That's going to bring down a 4 and we'll be left with 8ax e to the 4x. And now we want to take the derivative of the second term, which we will also have to use the product rule on. So let's start once again with this first part here and we'll take the derivative of that. So we'll have plus 8ax times e to the 4x. And then lastly, we will take the derivative of this last part here. So we'll have plus, that'll bring down a 4, 16ax squared e to the 4x. So we want to plug that into our differential equation here. So let's see what we'll get for that. So our coefficient of our y double prime term is 1. So we can just directly take that to be this here. So let's go ahead and rewrite that. So we'll have 16ax squared plus 16ax e to the 4x, where I combined these two terms here, and then plus 2a e to the 4x. So that's just our y double prime term there. And then we're going to get minus 8 times our y single prime, which we have written up here. And that is, let's see, we will have 4ax squared e to the 4x plus 2ax e to the 4x. And lastly, we're going to want to take 16 times our y sub p, and that is just ax squared e to the 4x. So that'll be plus 16 times ax squared e to the 4x. So right away we can see that in our y single prime term right here, we are going to pick up a negative 32ax squared term, which is going to cancel these two 16ax squared terms here. And it looks like I forgot an e to the 4x right here, but that is attached to that term there. Next, we have a negative 16ax e to the x that's picked up here. So that's going to cancel out these terms here. And that will just leave us with what's left right here, which is 2a e to the 4x. So we'll have 2a e to the 4x is equal to the left side of our original differential equation. So 2a e to the 4x is equal to, we had 2e to the 4x. So that just means a is equal to 1. So that gives us our particular solution, y sub p, which was, if you remember, a times x squared times e to the 4x, but our a is equal to 1, so we'll just have x squared e to the 4x. And like I said, if you wanted to solve the corresponding homogeneous equation, where if you set the right-hand side of that equal to 0 and solve, you could write the general solution for this differential equation. But because that's what we did in the last video, I'm going to go ahead and move on to our third problem. All right, so our equation for number 3 is y double prime minus 3y prime plus 2y is equal to e to the 3x times negative 1 plus 2x plus x squared. So we can see that the degree of our p of x term is going to be 2. And then from here, we want to find the roots of our characteristic polynomial, so we can see if any of them are 3. Well, our characteristic polynomial is r squared minus 3r plus 2, and that is going to factor as r minus 1 times r minus 2. And of course, neither of those roots is equal to 3, so we'll use the following substitution for our y sub p. So we'll have y sub p is equal to, well, we don't need to put an x in front of our e term because there are no roots shared, so we'll just have e to the 3x times a general polynomial of degree 2. So that'll be ax squared plus bx plus c. All right, so from here we are going to need to start taking derivatives, but let's go ahead and simplify some notation here so that the algebra doesn't get too messy. So I'm going to go ahead and let this part of underlined in blue be p of x. And we're going to need to take derivatives of this p of x in the future, so let's go ahead and do that now. So that means p prime of x is going to equal 2ax plus b, and p double prime of x is just going to be equal to 2a. So we can use those substitutions in the future. So let's see, y prime sub p is going to equal, we'll have 3e to the 3x times p of x, and that's going to be plus e to the 3x times p prime of x. And now we need to take our second derivative, so y double prime of p is going to equal 9e to the 3x times p of x. Then that will be plus 3e to the 3x p prime of x. And then we'll do our second term there, so we'll have plus 3e to the 3x times p prime of x plus e to the 3x times p double prime of x. So we can see that these terms here I'm underlining in blue will actually combine. So let's go ahead and make these substitutions for our y's into our original differential equation. So the coefficient for our y double prime is just 1, so we'll have 9e to the 3x times p of x plus 6e to the 3x, because those two terms combine, times p prime of x. And lastly, plus e to the 3x times p double prime of x. Our coefficient for our y prime term is negative 3, so we'll have negative 3 times, well, what was our y single prime? It was that there, so we'll have negative 3 times e to the 3x times p of x plus e to the 3x times p prime of x. And then lastly, we will have 2 times our y, but we already know what our y was, so we'll have plus 2 times e to the 3x times p of x. Okay, great. So let's go ahead and see what is going to cancel here. Well, we can see that these terms here are going to cancel because of that negative 3 times 3. That negative 3 is going to cancel this completely, and it would cancel this down to a 3. And I believe that's all we can cancel here. So what will we be left with? Well, we'll be left with 2e to the 3x times p of x. Then we'll have plus 3e to the 3x times p prime of x. And lastly, we'll have plus e to the 3x times p double prime of x. And that's going to be equal to our e to the 3x times that polynomial from the original equation, which was negative 1 plus 2x plus x squared. Kind of running out of room there. Okay, but we can divide out this e to the 3x from all of our terms here. And now we can go ahead and expand these p of x terms that we solved for earlier and relate the coefficients of the different powers of x to our equation on the right-hand side to solve for our a, b, and c. So on this first part here, we will have 2ax squared plus 2bx plus 2c. Then from the next term, we will have plus 3 times 2, which is 6ax plus, that'll be 3 times b, so 3b. And then lastly, from the last one, we'll have plus our p double prime of x is simply equal to 2a. And that's, of course, still equal to that quadratic there, x squared plus 2x minus 1. So let's go ahead and write these out to set us up to equate the coefficients here. So we'll have 2a, that's the coefficient of our x squared term. Then we'll have plus, we need our x terms here, so we'll have 6a plus 2b, that's going to be times x. And then lastly, we'll have 2a plus 3b plus 2c. So we can set up a bunch of different equations here. So the coefficient of the x squared term here is just 1, so we'll have 2a is equal to 1, which of course implies that a is equal to 1/2. For our second equation, we have 6a plus 2b, and that's going to be equal to the coefficient of our x term, which is just 2. But since we know that a is equal to 1/2, that means that 6a will be equal to 3, which means 2b is equal to -1, which means that our b is equal to -1/2. And lastly, we have 2a plus 3b plus 2c is equal to -1. Well, let's see what happens here. Our a term is just going to go to 1. Our 3b term is going to be -3/2. So we'll have 1 minus 3/2, which is -1/2, so -1/2. And that'll be plus 2c is equal to -1. So we can add that 1/2 over, and that will give us that 2c is equal to -1/2, which means that c is equal to -1/4. Great. So now let's go ahead and substitute this a, b, and c into our original y sub p. So we'll have y sub p is equal to e to the 3x times, let's see, we have 1/2 x squared minus 1/2 x, and then finally minus 1/4. So that is our particular solution to this differential equation. And let's go ahead and move on to our fourth and final problem. All right, so for number 4, we have y double prime minus 4y prime plus 3y is equal to e to the 3x times the polynomial 12x squared plus 8x plus 6. Now we can notice right away that the degree of this polynomial here is going to be equal to 2. And we can go ahead and find the roots of the corresponding characteristic polynomial as well to relate them to this 3 here. So we have r squared minus 4r plus 3 is equal to 0. But that's, of course, factoring to r minus 3 and r minus 1, which gives us the roots r equals 3 and 1, which means we have one shared root. So that means our suggestion for our y sub p is going to equal x times e to the 3x times ax squared plus bx plus c. And recalling from the last problem what our derivatives of that p of x are, we are going to use them once again. So we'll have that p prime of x is equal to 2ax plus b. And p double prime of x is equal to 2a, where of course this is our p of x. So let's go ahead and take some derivatives here. So we have y prime of p is going to equal to, we're going to have to use the product rule a bunch of times here. So let's start with the first part. So the derivative with respect to the very first term, which is our x, is going to be 1 times the rest. So we'll just have e to the 3x times p of x. Then the derivative of the second part is going to be the derivative of e to the 3x. So we'll have 3x times e to the 3x times p of x. And lastly, we'll take the derivative of the third part, which is just our p of x, and we'll have plus x e to the 3x times p prime of x. Now for our second derivative, y double prime. So starting with our first term, that's rather easy. We will have 3e to the 3x times p of x. That's going to be plus e to the 3x times p prime of x. So that's for our first term there. For our second term, taking the derivative, we will start with our 3x term. So we'll get 3 times e to the 3x times p of x. Then moving on to our e to the x term, we'll have plus, that 3 will come down, so 9x e to the 3x times p of x. And lastly, taking the derivative of our p to the x, we'll have plus 3x e to the 3x times p prime of x. So that finishes the derivative of that term. And then we can do the last term. So we'll have the derivative of the first, which is just x, which is 1. So we'll have plus e to the 3x p prime of x, plus the derivative of the second term, which is our e to the 3x. So we'll have plus 3x e to the 3x times p prime of x. And then lastly, we will take the derivative of our p of x term. So we'll have plus x e to the 3x times p double prime of x. Now let's see if we can identify any like terms in this mess from our y double prime. So we can see that this is a like term with this, as well as these two being like terms. And then we also have that these are like terms. And that just leaves those two at the end, which have no like terms. But I'm not going to go through all the algebra this time because it gets pretty messy. But when you finish with the problem, you should get that your particular solution y sub p is equal to x times e to the 3x times 4 minus x plus 2x squared. So that finishes this last problem off. Like I said, you can do the steps in between in the middle for homework, and I think that's a good place to stop.